Hello, my name is Dr. Jonathan Barron, and I am here to talk to you about my research in nuclear physics. I study what's called experimental high-spin nuclear physics using gamma-ray spectroscopy. In nuclear physics, just as you would expect, we study the structure of the nucleus of the atom. In gamma-ray spectroscopy, we create nuclei in excited states, and we use those excited states because they emit gamma rays to learn about the atom based on the gamma rays that they emit. The star subject of my doctoral research was from holmium-157. Holmium is a rare earth metal, number 67. So, to start off with, I would like to talk about why I study. What's the application of all this, you might ask? Twofold. First of all, the more experimental studies progress, the more equipment needs to progress to keep up with them. That equipment will eventually be used by other people in other fields. I think that the equipment that we use in creating excited nuclei is really cool, and I also think that the detectors are really cool. But also, the same detectors that we use to track gamma rays in a laboratory setting can also be used to find radioactive materials out in a field. The second thing that I like about studying is that we're advancing human knowledge. Every time we study a nucleus, we find a greater piece of the puzzle of the general structure of the atom. Now, mind you, it could be possible that one nucleus that we study could have really interesting and exciting results in it, but that's less likely. It's entirely possible that a nucleus could be used as a really good new type of battery for storing energy, but I'm not sure which one that would be. If I knew what it was, I would be studying it, surely. So, we're just trying to advance human knowledge, and hopefully at some point in the future, all of this gamma-ray spectroscopy stuff might be used in our day-to-day lives, like MRI or something. Earlier, I was talking about exotic isotopes. Isotopes are versions of atoms that have either more or fewer neutrons than they ought to. Think about carbon-14 and carbon-12. Carbon-14 is 2 more neutrons and also less stable. Exotic isotopes are even more short-lived than carbon-14. They break apart shortly after they're made. We make these isotopes by smashing atoms together, creating new isotopes. Acceleration is needed just to force the atoms together to overcome the Coulomb barrier. Around the nucleus of the atom, there's a bunch of electrons, and the shell of that electron is creating a force which stops 2 atoms from just naturally joining each other. It's sort of like how when I move my 2 hands together, they don't just become new atoms. The Coulomb force is what's holding them apart. Now, in order to accelerate beyond the Coulomb force, we need a lot of energy, but we've created even better and better accelerators that can go even beyond the amount of energy needed to overcome that force, and in doing so, we can create exotic nuclei with tons of energy in them. So I studied holmium-157, which was done at ATLAS, at Argonne National Laboratory. ATLAS is the name of their accelerator system, and it fired a beam of chlorine-37 at a target of tin-124. So this was made by accelerating the chlorine at over 185 million electron volts. Now, when this happens, at first to cool down, the holmium-161 that's created as a result needs to spit off neutrons to lose energy. But at some point, around holmium-157, exuding a neutron would be too much energy lost. So instead it starts emitting gamma rays. And when it emits those gamma rays, we've made it so that it's already stuck inside a gamma ray detection system in order to catch those gamma rays. We used what was called gamma sphere, which still is the most powerful gamma ray detection array in North America. It can have as many as 110 detectors inside of it, and it covers in a full circle around the target. And so all of these gamma rays that get emitted are captured. When gamma sphere captures one gamma ray, it opens up a tiny time window which captures all the other gamma rays from different parts of the detector that are captured at the same time. This creates what's called a coincidence window. After it reaches the lowest spin it can possibly get to, lowest energy it can possibly get to, then the holmium-157 nucleus breaks apart. We're no longer concerned with it at that point. So what we're now concerned about is forensics. Gamma spheres created a database of what gamma rays happen at the same time as other gamma rays. By looking at the relative intensity, the proportional number of times that these gamma rays were observed, we can get a sense for the structure of the atom. If the pattern of gamma rays were regular, then that wouldn't really mean anything. It's expected. It would mean that it's got a normal structure and no changes are happening. But when we have these sharp changes in energy, we expect that that also corresponds with a deviation in the change of the spin, and that also something else in the nucleus is changing. We expect that a proton or a neutron is being excited to a different energy state. So anyway, after a long bout of analysis, we get a sense of what the structure of holmium-157 is. And in these studies, we found very similar structures to, but different structures from, erbium-158. What we found are, in general, right, holmium-157, when it's at medium or high, or it's at medium or low amounts of spin, it is oblate, like a frisbee. But at higher amounts of spin, like over 65 h-bar units of spin, it is triaxially strongly deformed. And a triaxial deformation, that is really something special and difficult to describe. But ultimately what's important is that it's got the same properties, holmium-157 has the same properties as erbium-158. And a lot of what that means is that the deformation caused by it having 90 neutrons is what's really important. Thank you for